All right, our next talk will be given by Puja Das, talking about remote sensing, data-driven artificial intelligence for precipitation nowcasting.
Hello. Hello all, thank you for giving me the opportunity to present. I am Puja Das, a fourth-year PhD candidate in Northeastern University. I am presenting on behalf of my team. The title of our project is Remote Sensing Data-Driven Artificial Intelligence for Precipitation Nowcasting. Here you can see our team members. We have development partners, Kate and TJ, and stakeholder partner from Tennessee Valley Authority, and Oak Ridge National Laboratory, as well as Research Triangle Institute. In Northeastern University, I and August are working with our PI, Professor Aurab Ganguly. It's a Category 1 project that started last year, and it primarily funds me. I am starting with our primary stakeholder, TVA. So TVA manages the Tennessee River system. It has a length of 652 miles and watershed of 40,000 square miles. They provide electricity to 153 local power companies, and they have 29 hydroelectric dams and 20 non-powered dams. I am showing one of the dam here because it is one of our main study area. It's a Bear Creek Dam. Actually, very recently we got to visit some of their dams. So this is Norris Dam, which was the first dam that they ever built. This is another dam, Douglas Dam. We got to visit their operations and control center, the sluice gates, the power generation units, and I was very excited to visit all of them. This is our rain team with the TVA guys at the dams. So we are basically majorly collaborating with the River Forecast Center. The River Forecast Center is staffed 24/7, 365 days a year, and they monitor the river system to any changing conditions to the river or weather system. So we had a week-long discussions with them about what the models they're using, what are their daily day-to-day operations, and what type of products they need, and so on. So two summaries or lessons learned from this visit, I would say, first of all, we got to learn about the relevant data and case studies of different region. For example, here I'm showing the quantitative precipitation forecast from a flood event in Bear Creek Dam. In the first image, you can see the observed precipitation, and the second one is showing the QPF from the state-of-the-art numerical weather prediction models. And you can see the difference here. Not only they've missed the intensity of the precipitation, but also the locations where it actually happened. We also got to know about their requirements. So although they want to work with extreme events and they need to know the probabilities associated with these extreme events, for their operation, they can use only one number forecast so that they can input that model information into their models and find out what would be the output for the dams and do their operations. And we also got to know about some of the specific hydrological metrics that they use, such as this flood guide curve. So you can see the guide curve here. This is the storage of water behind a dam in a reservoir. This is showing the 12 months. The x-axis is showing the 12 months of a year, and y-axis is showing the water level. And the green line here, it's very faint, but the green line here is showing the flood guide curve that they want to maintain throughout the year. And the black line is showing the observed. So they want to close the gap between these two lines as much as possible, because if there is a high gap, that means there was flood, and they that can sometimes overtop their dams also if they go very high. Starting with another story that they shared with us, it was a record-breaking rainfall in Middle Tennessee, and it broke their past record of 24-hour rainfall of 13.6 inches. There was a 17 inches rain throughout the day, and I was trying to find out what would be the return period of this event, and I could not find the curve in these lines, and then asked them what is the return period, and they said that it is more than 10,000 year return period event, and as a result, it washed down an entire neighborhood and 21 people died. Now I'm sharing the QPF from the numerical weather prediction model of that event. Here the colored lines are showing the QPF from different sources, and the green line here is showing the HRRR, which is high resolution rapid refresh and the state-of-the-art numerical weather prediction model. The black line is the observed. So you can see there is a very huge difference between the observed and the prediction from the numerical weather prediction model. So currently they discontinues the operational use of HRRR and they use the QPF from Lower Mississippi River Forecast Center or ECMWF from European Center. Now, sharing a little bit of the literature review, the precipitation nowcasting has been going on, or the importance of it has been discussed for a long time now. I'm sharing two papers here, which from Professor Ganguly and his supervisor and supervisee at 2003 and 2020. So they were looking at that hybrid physics AI approach and deep learning methods can improve QPF over other baseline methods. And in this figure, I am showing that the information content usually goes down if we increase the forecast lead time, and the solid line is showing the theoretical limit of predictability. Now, nowcasting usually starts at very high information content because it's fed with the observed data set, but soon it goes down. So we are trying to improve this nowcasting and trying to go it as close as to the theoretical limit of predictability. And also the physics of precipitation that we know of convective and orographic precipitation that is important for Tennessee Valley in the Appalachia. Only the incorporation of physics it's hard to improve our prediction skills just only with the physics. However, we can use physics to inform the interpretation and also inside the machine learning model to have better forecast now. Now we have divided the scope and task of the project into three main scopes. So first of all, we would develop hybrid radar-based physics AI ensembles. So here we would look into both baseline approaches as well as state-of-the-art approaches. So baseline approaches would be persistent, advection, optical flow, and so on. And state-of-the-art approaches would be generative AI and hybrid physics AI methods that has been coming. We are also thinking of creating an ensemble of this generative AI models and then look into Tennessee Valley Authority, how they perform in that region. And next, we would develop and evaluate satellite-driven AI ML products. So for this, we would generate quantitative precipitation estimation using computer vision, and then precipitation forecasting using generative AI and computer vision. And we would like to see the value of satellite information, content, and predictive skills, and if they can improve the radar-based precipitation forecasts. And finally, we will generate stakeholder relevant information. So not only we would look into mean, but extreme events that they are dealing with, and also percolate the skills to end users and evaluate the metrics that are important to them. So this is showing all of them together. I'm sharing a little bit about the tasks here. So the first task was to develop hybrid physics AI ensemble that is radar based. So we would first of all do subtask 1.1, which is the meta-analysis of the literature and best practices. And we would develop a suite of model ensemble, which we will adapt and evaluate to the needs of TVA. And through this, we would develop open access data and softwares. So while doing some background research here, we saw that currently people are using physics-free prediction-based predictions based on instantaneous radar. So instead of numerical weather prediction models, this has an advantage over this because it uses instantaneous observations. And this study came out by Google Research. They used UNet-based CNN model, convolutional neural network model, and they are saying that their physics-free approach works better than the numerical weather prediction models. Then in 2021, another Nature paper came, which shows that deep generative model outperforms even the CNN models. This is also a physics-free approach. And finally, very recently, this paper came in Nature again, which says that physics-based deep learning method, which they call nowcastnet, shows improvement over DGMR also, the previous work. So here we can see very extreme precipitation event, and they can find out if it was advective precipitation or convective precipitation, and they are showing improvements over DGMR and pi steps. So they have been incorporating physics such as conservation rate of mass conservation of clouds or log normal rate of precipitation inside their models to have better predictions. Now coming to the task 2, as we said, we will generate QPE, QPF, and then evaluate based on our end use. I am focusing a little bit on QPE because that's what we have been doing in the past year. So we have been using satellite images as well as radar images. So we are using multi-radar, multi-sensor, which are available at very high resolution. And then we are using GOES 16 and 17 satellite imagery. And then we are matching the exact time to create the data set, and then creating small patches to run inside the model. For model, we are using a computer vision techniques, convolutional neural network model. Here we are using the 10 infrared bands inside the GOES 16 and 17 satellite images. And we are using this as training data set, and MRMS, we are using this as a training level. And as an output, we are getting the precipitation rate maps, which are similar to the MRMS one. So we are trying to get the MRMS precipitation rate maps from the satellite images. Here is the model architecture. We are using 4 convolutional layers, and we are getting the precipitation rate maps here. Coming to the results, some of the results. So we started with very small training samples, only 20,000 samples, and this is the actual precipitation. And the last column is showing the prediction. So we can see the predictions are missing at a lot of location, and the intensity is not quite there. So we thought of increasing the precipitation training samples, and we did that, and we are still seeing that intensity is not that much improved for even 800,000 training samples. So we are looking for the reasons why it happened. And then we saw that we were using GOES 17, and GOES 17 actually faced a loop heat pipe issues. For that, some of the data set was not in usable condition, and it was not written anywhere. So we learned it hard way that we have to use GOES 16 or 18. So we are doing that now. Next, we would use QPF, and we would generate QPF. That is our final product, and we will do that in the next coming years. And we are also thinking about different stakeholder metrics and that is relevant to them. So all the studies that have been coming out, they are focusing more on meteorological metrics, but our stakeholders are helping us to understand that there are hydrological evaluations also, and that also needs to be done. So we are doing that, and and in part of that, we are also developing stakeholder-driven metrics such as a flood guide curve, and a way to evaluate evaluate the alignment of flood guide curve with the precipitation forecasts. And finally, we will develop cost metrics for flood impact assessments. I'm going a little faster here. These are the future works that we would do. So we would do an evaluation based on 3 terms, as Murphy said in 1993, that a good forecast should be evaluated based on these 3 terms, that is appropriate set of tools, or appropriate statistical metrics, or in the context of end use. So in terms of statistical metrics, we have been showing here some of the common or standard ones, such as probability of detection, false alarm ratio, bias, MSC, RMSC. Based on space, we will look into spatial correlation and so on. But we will also look into some of the key performance indicators for extreme events, such as return period, recurrence intervals, and also we would look into if any other variables has an impact on the precipitation extremes, and we would like to find those out using entropy and mutual information, as well as relative entropy, such as Kullback, scale divergence, and so on. And finally, this is task 3.2. We would also evaluate the impact of precipitation forecast on water resources. With the flood guide curve, they have data of plus 10 years of extreme events, and they have examples of successes and failures of HRR, where they succeeded and where they failed. So you would learn from those events, and they have been sharing those data sets with us, and this is very helpful for us to analyze not only the physics behind these events, and also where we can improve the forecasts for them. So, thank you for this.
We have time for one quick question. Barry?
Thanks for the talk. That was really interesting. So regarding the principle of doing physics-informed machine learning being better than just a physics withholding machine learning, does that help to incorporate information about non-stationarities within extreme events? You know, is that implicitly or explicitly baked in somehow?
Yes, that's one of the important things that we're seeing, that even if I'm sharing a backstory here, even if we are looking into the return periods and return curves, those think that the precipitation is a stationary event, and then there is no climate change, and it hasn't been increasing now. So yes, it's we should incorporate the non-stationarity also, and for that, using physics, not only physics but the examples of past events through a machine learning model would help it to understand that even if the physics hasn't changed, but there has been more instances of extreme events which it can learn from the machine learning models of past events.
Great. All right, we'll move on to our next talk. Thank you, Puja.